Start off actually with this quiz that's in front of you. And what I want you to do, just to see where you are, we haven't learned R or S yet. We're going to do that today. But before we do, let's have you take a look at question number 1 and identify all the molecules that are chiral. And I also want you just added, I want you to also identify all the stereocenters. And for those just walking in, we are identifying stereocenter. We're doing problem number 1 on the quiz. Which are chiral and where are the stereocenters? There we go, that's better. Oh, shoot. Okay, how you doing? Do you need more time? Yes? Okay. Any questions or worries, anything that's tripping you up that I can help with? Just a ton of molecules? Okay, keep working. Okay, who needs help with remembering what chiral even means? A little bit? Yeah, that's okay. Chiral means not the same as its mirror image. Like your left hand and your right hand. Different reflections of each other, but not the same. So one test, and this test takes forever, that you can use to determine whether something's chiral or not is draw the mirror image and then see if you can rearrange it to see if it's the same thing. There's some shortcuts though. Anybody know some shortcuts? What's a good shortcut for identifying a chiral molecule? You look for symmetry. If it's got a plane of symmetry, it's not chiral. And that's interesting because that's a good way to detect compounds that have stereocenters but are nonetheless not chiral. If a molecule has a plane of symmetry in it, by definition, it's the same as its mirror image. So let me just demonstrate that here with a molecule that we talked about last time that has two stereocenters. It's pretty clear that what's on the left-hand side of this molecule is the same as what's on the right-hand side. This is mirror symmetry. And if we draw the mirror plane here, as we've done in the past, if the molecule has a mirror plane of symmetry, it is by definition the same as its mirror image. Always. So if you can identify a plane of symmetry, it's not chiral. Does that help you with one of these? Which one of those has a plane of symmetry? Yeah, and it actually has the word meso in the name, so if it's got the word meso in the name, it's probably not chiral. It's got a plane of symmetry. There it is, right there. Those are stereocenters, but the molecule's not chiral because it's the same as its mirror image. Do you know any other shortcuts for identifying chiral molecules? Go ahead.
Looking for the number of stereocenters.
Right, number of stereocenters. So what does that tell you? If it has one, has to be chiral, always. If it has more than one, you got to check because it could be a meso compound. So which of these have just one stereocenter? Oh, let's look at citrate. Is that a stereocenter? It looks like one because the dashes are wedges. Why is that not a stereocenter? Yeah, what's on the left is exactly the same as what's on the right. A carbon that is bonded to two of the same thing is not a stereocenter. Can't be a stereocenter. So yeah, citrate is not chiral. Good. How about isocitrate? You're not willing to commit because you're worried. That's okay. Commit. Chiral, good. And it does have stereocenters. Where are they? You got this one? Yeah, and then this one. Interestingly, these two are isomers of each other. You move the OH group over one, suddenly you break the symmetry. But yeah, we got two stereocenters. Now, go ahead.
So if they don't have plane of symmetry and they have more than one stereocenter, do you need to just draw the reflection?
So what do you do here? It's got two stereocenters. The plane of symmetry isn't obvious. I would say you can draw the mirror image and see if you can flip it over and make it the same thing. I want to be careful with if you can't see the plane of symmetry, because there would have been a way that I could have drawn mesotartaric acid, which would have totally concealed the plane of symmetry. I could have drawn exactly the same molecule like this, and some of you would have been tempted to say that's chiral because I can't find a plane of symmetry. But if you rotate around this carbon-carbon bond, you get there, and then you see the plane of symmetry. So you have to be a little bit careful with 2 or more stereocenters. It might be chiral. Look out for meso compounds. One way to detect the possibility for a meso compound is if you notice that carbons A and B are bonded to the same kinds of things, then there's a possibility that it could be a meso compound. Yeah, so I had.
Do wedges and dashes matter when you're looking for a plane of symmetry? Like, do you have to have the same wedges?
Yeah, wedges and dashes matter when you're looking for a plane of symmetry. In other words, if the molecule had been this, that one is chiral.
So, like, on citrate, the right side, even though it is the same atoms as the dash.
Oh, so citrate, does that matter? The thing about citrate is you don't even have to look for a plane of symmetry because there's no stereocenter. But I agree with you, the way that we've drawn it is not, it doesn't look perfectly symmetrical. If you use the claw innator and grab the oxygen and pull it up towards you a little bit, that's going to bring this dash sort of up into the plane of the page, and then it is perfectly symmetrical. Some of this may require, some of this is 3D spatial imaging, and a model set can really help you with this, at least in the beginning. However, you want to practice with the model set before you go in the testing center, because if you're in the testing center and you get your model set out and you're stressed out, you're going to spill that thing all over the place. And then suddenly you're even more stressed out. So, okay. 1 stereocenter must be chiral. 2 stereocenters, watch out for meso compounds. In this case, citrate is chiral. Succinate is not. Why not? No stereocenters. How about glycine? Similarly, no stereocenters, can't be chiral. Proline. Chiral, because you got a stereocenter. Yep, good. Beta-D-glucopyranose, chiral or not? Chiral, and you know that because it's got stereocenters and there's no plane of symmetry. And you could go through the process of drawing its mirror image and flipping it over and trying to see if you could line it up, but you wouldn't be able to. Did I see a hand? Okay, and then glyceraldehyde, 3-phosphate, has to be chiral. Okay, good. So, chiral or not, 1 stereocenter, it has to be chiral. 2 stereocenters or more, it might be chiral, but you better be careful. And the standard for chirality, if you're confused, the thing to go back to, if you can't solve a problem, forget about the stereocenters and just draw the mirror image and see if you can flip it over, twist it around, or in any way make it the same as its mirror image. Okay? Because that's the fundamental definition of chirality. Questions about that? Yeah.
So does not having a plane of symmetry indicate that it is chiral?
Does not having a plane of symmetry indicate that it is chiral? If it has stereocenters, if it doesn't have stereocenters, it's not chiral. If it doesn't have stereocenters, you'll be able to identify a plane of symmetry. If it has stereocenters and has a plane of symmetry, it is not chiral. But as I said, it is easy for me to conceal the plane of symmetry by simply drawing the molecule in a different conformation. So you should be careful of that. Yes? Yeah, I saw a hand. No? Yeah?
Oh, yeah. For that, how would you tell that it's chiral versus not chiral on 1 for each of these things?
You mean this one?
Yep.
So if I had drawn it like this and I concealed that it had a plane of symmetry, how could you have detected my evilness? Okay, let me show you two ways to detect the evil. I mean, the real answer is follow the light of Christ, which will help you detect evil, even for me. But, okay, so two ways. The first way is perhaps the one that will take a little bit more time, but will always work. Just draw the mirror image. Okay, so everything on the left is a reflection of what's on the right and vice versa. And now we see whether we can twist it around, rotate it around, flip it over in some way to get the same thing. So you could try the steering wheel innator, where we rotate it around like this. Okay, so that appears not to have worked. That doesn't exactly look like it worked. What about the pancake flip innator? So let's take the molecular spatula, slide it under, and let's flip it over this way. If we do that, here's what we would get. So this OH group, since we flipped it over, should now be a wedge. And this OH group, since we flipped it over, should now be a dash. And you can see now that those are the same thing. Okay, so that's one way. The second way is for you to realize if I look at carbons A and B in the middle, I notice that A is attached to an OH group, and so is B. And I notice that A is attached to carboxylate, and so is B. So that should set off just a flag in my head. There's the potential for a meso compound. I need to look for it. And the thing that will help you most to see this will be to see if you can rotate around the bond between A and B in such a way as to bring similar groups eclipsed with each other. So I'm rotating around that carbon-carbon bond between A and B so that now the green carboxylates are eclipsed with each other. I left carbon B basically exactly the same as it was. I twisted carbon A. Because I've twisted it around, the OH group on carbon A is now a dash rather than a wedge, and there the plane of symmetry reveals itself. Okay, so that's one way you can do this. Okay, while we're on it, let me just disclose, full disclosure, all of my secret evil meso tricks, shall we? Okay, one secret evil meso trick, aside from conceal by rotation, one secret evil meso trick is to conceal in a chair. This is actually one on your problem set, but it is so diabolically evil that I cannot resist. We're going to talk about it now. So, oh, fine, I don't want methyl groups. Let's do OH groups. This question could be formatted in a couple of ways. I could draw just this one and ask you, is it chiral or not? Or I could draw both of them and say, what is the relationship between these compounds? Are they the same compound? Are they enantiomers? Are they diastereomers? Now, if you look, this is a stereocenter, and so is this. And it looks like this is the mirror image, and it is. And now you've got to try to figure out, are they the same or not? And it sort of looks like if I put an axis down the middle of the 6-membered ring and twisted it around, it looks like I probably couldn't line them up because then this OH is going to swing around in here and be axial, and this OH is going to swing around here and be equatorial. In other words, if you looked at those two and you tried to play with it for a while, it might be difficult for you to see how they could possibly be the same molecule. But there's a trick. And the trick is, that you may not see, is this is actually just the other chair. Isn't that evil? So evil. And if we did the chair flip on this one, sorry, I'm gonna sneeze. Do you know I was actually in a faculty meeting like a couple weeks ago, and it was a really serious meeting. We were discussing a very serious issue, and in the middle of it I had to sneeze, but I found just before I had to sneeze a piece of apple in my teeth that I was sort of playing with, and I tried to hold the sneeze in, and I ended up going in the middle of this very serious meeting, and I was very embarrassed. I had to apologize to my colleagues. It was being recorded. The meeting was being recorded, so anyway. Do you want to see the recording? No, I think it's been destroyed maliciously. Anyway, the chair flip here would be up carbons become down and down carbons become up. We'll call this carbon 1 and 2. This is now carbon 1 and 2 after the flip. Axial switches to equatorial. Now I think you can see that if we spun this molecule around, did steering wheel action, we could bring carbon 1 here and carbon 2 there. So sometimes two chairs will appear as mirror images, but they're actually just the other chair of each other. If you want to avoid this entirely, none of you probably are old enough to have seen the Dick Van Dyke Show. If you watch like old-timey TV, there was a show in the 60s involving Dick Van Dyke and Mary Tyler Moore, and Dick Van Dyke would always come into the house, and half the time he would fall over the ottoman, and the other half the time he would sidestep the ottoman like that. So you want to sidestep this problem. Avoid the chair entirely. Simply draw the chair as it would appear from above. So if we do that here, you would see that this molecule looks like this. And if you do that here, you would see that the molecule looks like that. Then it is pretty dang clear that those are the same molecule, right? So often, if somebody draws you a cyclohexane ring like this, like in the chair form, just draw it from above, and then the relationships become easier. Okay, other questions about that? Okay, evil, yes, go ahead.
With those two, is it just, you would like, the other one you would turn over and then make them,
Yeah, all you do is like this.
okay.
Yep.
And then the chair one, I am struggling to see how the chair flip is the same as
Right, and I think, are you okay on the chair flip process?
yeah.
Okay, so all you need to do then is grab a hold of, that's my terrible cartoon hand. And you're going to rotate this around by 120 degrees like a steering wheel. And as you do that, carbon 1 here is going to come here, and carbon 2 here is going to come there. If it's not making sense, come talk to me. We can build a model, or you can build a model and work through it, because I agree it's hard to see on paper. All right. Diabolical evil trick, this is maybe the worst one, is, and then we need to practice. Diabolical trick 3 is to draw a Newman projection. Oh man, I hate to disclose this one because it's so fun. All right, so I could draw, let's see, I'm going to need another page. Could draw something like this, and then I could even draw its mirror image, and I could say, is it chiral or not? Except I'm not drawing a mirror image. Thank you, yeah. Oh, still no. That better? There we go. All right, so these two are mirror images of each other, but the question is, are they the same thing? I might have just drawn this for you and said, is it chiral? Or I could have drawn both of them and say, what's the relationship between those two molecules? Are they enantiomers or diastereomers? One thing to help me out in terms of my radar for this kind of trick going on would be to notice that carbon A in the front and carbon B in the back are attached to similar sorts of things. There's chloros on both of them, and there's methyls on both of them. So I at least acknowledge that there is the chance that there might be a plane of symmetry here. It might be a meso compound. Now, as it is, I can't really see that. I can't really see the plane of symmetry. I could try to, in my head, flip around the Newman projection and see if it's the same thing, but that's really hard to do. Newman projections are sort of hard in the first place. Trying to manipulate them in 3D, take one and spin it around is, I mean, if you build a model set, that can work. But I just want to show you a quick way to deal with the Newman projection. Take the carbon in the back. Remember what I told you earlier, you want to redraw the molecule in a way that the similar groups are eclipsed with each other, and if you can, and then that can reveal the meso compound. So I'm going to take the chloro in the back, and I'm just going to rotate that carbon by 180 degrees. And if I do that, that should turn the carbon in the back to be eclipsed. That should turn each group in the back to be eclipsed with the groups in the front. See what I'm doing? So the chloro in the back should now be eclipsed with the chloro in the front. The methyl group in the back is going to rotate around 180 degrees to be eclipsed with the methyl group in the front. And then the hydrogen in the back is going to rotate 180 degrees to be eclipsed with the hydrogen in the front. Okay? Follow that? Do you see how I did that? And you could do the same thing over here. Now, where's the plane of symmetry? It's the page, right? The carbon in the front is a reflection of the carbon in the back. Yes? Go ahead.
Does it also work, or is this not about just look at it 2D and just like flip it over? Is that
Can you look at it 2D and just flip it over, and will that work? So you're saying, can I take this as though it were 2D? Can I pancake flip it? If you do it right, then yes. So we'll pancake flip this. The carbon in the back, carbon B, is now in the front. If I flipped it, that carbon ought to, if I flipped it correctly, that carbon ought to look like this. And then you could see, yes, it's exactly the same thing. Yeah, so if you can do, did I do it wrong? No, I think that's right. If you can reason through that, and if it works for you to do that, then sure, no problem. Okay, so you can see that the plane of symmetry is the page itself, and you can see how these two are the same thing. Yes?
So does this example have a stereo center?
Does this example have a stereo sender? Yes. If I were to draw this molecule from the side, this is what it would look like. And these two are stereo centers, but this is an example of a meso compound where there's a plane of symmetry. So yes, it has stereo centers, but no, it's not chiral. Yeah?
So could another way to solve it be just draw it like that?
Sure, another way to solve this could be to draw it from the side. Now, sometimes people struggle with this, but if you're okay in interpreting Newman projections, just put your eye in the plane of the page, look like this. I would have drawn it, I would have drawn it like this, and then you could rotate around and find the plane of symmetry. So actually, there's often a lot of ways to solve this. You need to find whatever way works. You're going to have a lot of options, building models, manipulating things on paper. But yeah, the three major ways for me to conceal evil meso compounds is by rotation, by putting them in a chair, and then by putting them in a Newman projection. So practice, because that'll be useful. I am evil, but at least I disclose my evil to you ahead of time. With that in mind, let's apply what we've learned and describe the relationship between these compounds. Okay, so you've got choices. They could be constitutional isomers, that is different connectivity. They could be enantiomers, they could be diastereomers, or they could be the same molecule. To help you on definitions, remember enantiomers are mirror images, but are not the same. Diastereomers are stereoisomers, but not mirror images, or that is not enantiomers. Okay, getting close to ready to start talking about them? How about these two? Same. All right. That was a softball that I threw at you there. It was obvious that those are meso compounds. How can you tell? Plane of symmetry and pancake flip the one on the bottom, and it's the same thing as the one on the top. I will not be so nice to you on the exam, so be prepared. But those are the same compound. Okay, how about these two? Diastereomers, good. How did you know they were diastereomers? Yeah, that's actually a really useful tool for diastereomers. Diastereomers are different at least one, but not all stereocenters. So do you notice how all the stereocenters on the one on the bottom are identical except for the one highlighted in orange? So that's one way you can, that's a quick trick you can use to identify diastereomers. They have to be different configuration at least one stereocenter, but not all. Okay? Okay, how about these two? Next one. Enantiomers, okay, that is easy to tell because it just has one and only one stereocenter and they have opposite configuration. So that one's easy because if it's just got one stereocenter, it's got to be chiral, and if it has opposite configuration at that one stereocenter, it's got to be an enantiomer. Enantiomers, another trick is they have to have opposite configuration at all stereocenters. But I'm going to put an asterisk on that, and we're going to come over here and say, beware the meso compound, where it will look like they have opposite configuration at both stereocenters, but they're the same compound. Okay, how about these two? Next. Some confusion. Some of you said constitutional isomers, some of you said diastereomers. The right answer is diastereomer. Okay, all cis-trans issues about pi bonds are diastereomer issues. This pi bond is E, this one is Z. And you should be having a little bit of PTSD because this problem was a nomenclature problem on your exam and it confused some of you who were trying to figure out what the heck to call this double bond. And the secret was it is neither E nor Z, it's just because it's got two of the same thing there. So yes, E and Z configuration issues are always diastereomer issues. All right, how about these two? Constitutional isomers, that means their constitution or their makeup or their connectivity is different. Okay, different connectivity. Great. All right, so what we need to do in the last 10 minutes is to figure out how to talk sensibly about, yes, go ahead.
Sorry, what is the difference between the pancake flip and the mirror image?
What is the difference between the pancake flip and the mirror image? For a molecule like this, the mirror image is to draw everything on the right of the mirror as a reflection of what's on the left of the mirror. If I instead pancake flipped the molecule on the left, what I would end up with is something like this. Sorry. I did that totally wrong. So pancake flipping is literally taking one molecule and just looking at it from another side. And you can see that the pancake flip of the molecule on the left side is not the same as the mirror image. Do you see how the CLs and the H's line up, but the F's and the BR's don't? Yeah. All right. So in the last little bit, we need to learn to talk about stereocenters. You've seen that for each stereocenter, there are two possible configurations, and we need to introduce a nomenclature tool for describing those configurations, and that is R versus S. Okay? So, let's talk about how to do this. We'll start with this molecule here, where this is a stereocenter. It's useful if you're going to do this to draw in the hydrogens that are implied but not shown. Okay, and then what you will do is we're going to assign a priority number 1 through 4 to all of the things attached to that sp3 hybridized carbon. And we're going to do it using the E and Z rules like you've done before. So if you got E, Z stuff wrong on the exam, on the first exam, you might get R and S stuff wrong on this exam, and so it's a good time to learn it again. Remember that it's an atom by atom consideration and comparison. So I'm going to compare nitrogen versus hydrogen versus carbon versus carbon. And I'm going to give them priority numbers 1 through 4. Now it's clear that hydrogen should be 4, and it's clear that nitrogen is heavier than carbon, so it's clear that nitrogen should be 1. It's not yet clear which carbon should be 1 because they're the same, so we do the tiebreaker procedure, which is to consider what it's bonded to. This is where some of you jumped ahead and made mistakes on the midterm exam 1. Some of you looked at a carbon like this and only saw the oxygen and said oxygen's heavier than carbon. You were right about that, but that wasn't the right time to make that comparison. So the right comparison is first, these two are both carbons. That's a tie. I don't know what to do, so I'm going to write down what each of those atoms is bonded to. The one towards the lower right is bonded to 3 times to oxygen and 1 time to carbon. This carbon is bonded twice to carbon and twice to hydrogen. And it helps to write them down in order of weight because we're going to go from left to right looking for a difference. We find it at the first letter, oxygen versus carbon. So oxygen wins. I guess I should have used a little bit of an X to indicate that it's a tie. Oxygen wins, so that makes this group 2, and then this group 3. Are we clear on that assignment? Okay. Now we're going to draw an arrow from 1 to 2, from 2 to 3, and from 3 back to 1, and we're going to annotate whether or not drawing that arrow is clockwise or counterclockwise. In this case, it's counterclockwise. The second thing we're going to do is ask the priority number 4 group, is it up or is it down? Is it a dash or is it a wedge? If it's down and it's counterclockwise, the correct configuration is S. If it's up and it's counterclockwise, the correct configuration is R. What most people do is they memorize the rules for where the priority 4 group is down in the back, and then they just remember to flip it if the priority for 4 group is up. Okay. Okay. And let me just, another way to formulate the rules is if the priority number 4 group is down, counterclockwise is S, and clockwise is R. Okay? So let's do this stereocenter on the adjacent amino acid. This is a dipeptide. You'll learn about it in 352. Let's go through it together. And it will help you to draw in the hydrogens that are implied but not shown on the stereocenter. Which is highest priority? Nitrogen, because nitrogen is heavier than carbon and heavier than hydrogen. Of the 2 carbons, which is higher priority? This one up on top. You can tell because this one is bonded twice to oxygen, once to nitrogen, and once to carbon. This one is bonded twice to carbon and twice to hydrogen, so the one on the top wins. 1 to 2, 2 to 3, and 3 back to 1. That's clockwise, and proton, the priority 4 group, is up. So it should be what? S. Good. Okay. You're going to need to practice that. You'll eventually get so you can do it pretty quickly, but in the beginning, you'll need to practice it. And so here's some opportunities. Why don't you do this one? Okay, you got some answers? What do you got? Still working on it? Oops. Okay, what's the configuration on carbon A? S. What about B? Also S. There's a theme here. All the stereo centers we've looked at so far are S. Good. Sometimes when I was a primary chorister, or even now at Special Needs Mutual, where I'm a music leader, we'll do snake singing, which is where we draw out the S's in all of our songs, and it's kind of fun. Jesus wants me for a sunbeam. Okay, if you want, take a picture of that quiz. I will post the PDF of this and a key today so you can do more practice. But don't forget to turn in your quiz on the way out, and I will see you Friday.